Thanks a lot. It's an absolute pleasure and honor to be here, and I hope that you enjoyed the conference as much as I did. Very brilliant talks till now. So my talk entitles Locating Flowing Conduits in Karst using Passive Seismic Approach, and I like to honor my mentor and co-author Crispin from DIAS. So this work, and shout out to ICRAG, as this project has been funded through ICRAG and Geological Survey Island and TII Transport Infrastructure Island were our partners in this project. And I really like to acknowledge Dr. Kuivahiki and also Dr. Ted McCormack for providing us with all the literature review and shape files of the caves that we needed throughout our study. I think you are familiar with the extension of Karst in Ireland through the brilliant talk from Dr. Hickey yesterday. So in the left map, you see the distribution of limestone in Ireland, and near half of Ireland is underlain by limestone. And where it is pure, most of this limestone bedrock has been karstified. And you see the karst features actually depicted as purple features in this map. So a study of the groundwater flow in karst is important from these different perspectives, including water resource management, and also in terms of groundwater flooding and geotechnical applications when constructing roads and bridges so that not to interfere with the flowing conduits in karst. For instance, you see an example of the groundwater flooding happened in Gorse and blocking the railway line for a couple of days or weeks. So how we are approaching actually this problem using passive seismic is that we believe that any kind of physical phenomena in a water system, including turbulency of the water flow, bed load transport, breaking waves, and any other phenomena can induce tiny ground vibrations that may not be actually felt by us, but it can be detected by putting seismic stations near a surface river, or in our case, subterranean water systems like flowing caves or conduits in karst. And then we record that data, we process that data, and then we can determine from which direction those signals are coming from. And that direction would be where the flow is, and in our case, that conduit. We used a range of seismic instruments throughout our experiments. On the left, you see the broadband seismometer, which is the most sensitive seismic instrument and globally used for earthquake detection. It is very sensitive, but as you see, it's a big and heavy instrument and it's not very easy to deploy. In the middle range, you see actually what is called short period seismometer, less sensitive than broadband seismometers, but easy to deploy. And finally, you see geophones, or in this case, smart solar nodes, which are the least sensitive, but still applicable in our studies. And they are very easy to deploy, and we have one component and 3 component geophones, and they can be deployed easily on the field for months for data recording. So before going actually to do the fieldwork and studying karst, to familiarize with what is the seismic signature of the flowing water, we did an experiment near Avoca River in Wicklow in 2019 by deploying 2 clusters of seismic stations called arrays, and also a few sparse seismic stations. And the main reason for choosing Avoca River for this study is the existence of 2 permanent flow gauges belonging to EPA. And the aim was that if we detect any seismic signal that is generated by the flow of water in Avoca River, can we actually correlate the seismic signal with the water flow or water level change? And if so, in that case, we can claim that seismic approach can be used as an indirect monitoring tool for determining water level change and also flow rates in rivers or in subterranean systems. So here you see an example of seismic data. So the background low amplitude signal is generated by the flow of water in river, and the high amplitude spikes are the cars or trains passing by. And the middle figure, called a spectrogram, shows the time evolution of the frequency content of the data. And as you see, the data is highly contaminated by cultural noise, as we were close to the Wicklow County construction site, and also near a railway line and local road. So it's very hard to detect the flow signature, but it's not impossible. So if you look between the frequency of 10 to 20, you may see a persistent signal that appears that belongs to the flow of water in the river. So once we detected this signal and we extracted this signal, in the bottom plot, we plotted actually this signal called tremor against the flow data that we downloaded from the EPA gauge. We observed good correlation between these two measurements, and that was very promising. So in the next step, we went we went for the study in Karst. The first site locates near French Park in County Roscommon. The cave we studied called Polnagran Cave. So the reason that we chose this cave is that it's actually simple sink to source cave, and it's shallow, within 5 meters subsurface. You see a photo of the entrance to the cave, and also the dye tracing that has been dyed here, and there are multiple inlets to the cave. So we did an experiment between 15th to 20th of December 2020 in this field, by deploying linear moving profiles of short period seismometers that are depicted as white icons here, and also the geophones that are depicted as blue icons. So the station spacing are 2 meters, and we could deploy 2 lines per day. And this is the overall actually coverage of the area by seismic instruments. And this is how the deployment in the field looked like. We basically dig a small pit, we bury the seismometer and put the data recorder, leave them to record data for a few hours, and then we deploy the next profile. So you see how the data looks like for the 24 stations of one of the profiles, the first profile that we deployed. So on top, you see the example of the seismic data, and on the bottom, you see the spectrogram. So similar to the river, we are looking for a persistent signal that belongs to the subterranean flow of water, and we are seeing that signal here that changes from station to station and also by time. And that's very interesting and reassuring. So once we detected the signal, we need to make sure it's really coming from subsurface. So we applied a method called Amplitude location method that is a well-developed method in volcano seismology to locate and track the magma flow in volcano settings. So basically, we assume that the flowing conduit is the source of the signal, and by putting the stations on the ground, we actually can measure the amplitude of the signal from the source to different stations, and through a grid search approach, we can then determine from where that signal is coming from. So here you see the final results of applying the method to different linear profiles, to all the linear profiles in this experiment. So the red actually here, the red in the misfit map shows the most probable location of the source. So what is interesting is that we noticed that there is a source along the dived actually cave, and also there is a secondary source to the northeast of this area that can be like a secondary water tributary here. So we actually modified our method to look for 2 sources at the same time to make sure that we are really having 2 sources, and that was correct. So we have 1 source along the dived cave and the other source northeast of the area. And also to make sure that the geometry of the actually stations that we deployed and also the method is working really correctly, we used the hammer shot data that we did for the refraction seismic study in this area to locate the hammer shots with this method, to see if we do the actually hammer shot near one of the station and we apply the method, can we really locate where the hammer shot is? And as you notice, the exact location of the hammer shots are depicted as a star here, and the misfit map, meaning the location of the hammer shot by our method, is depicted by the map, and they are very close. And the same is for the 2 source solution, and we are making sure here that the method really works fine. So the second site that we studied actually locates in Gort, County Galway. We studied the cave pull-to-fill to Puldillin, pull-to-fill sink to Puldillin rising, exactly near where I showed you the groundwater flooding in the first slide. This site actually is different from the first site in the sense that, as you see, the conduit is U-shaped here. And it can be very deep. At the greatest depth, it reaches to 60 meters subsurface. And it's most of the time throughout the year, it's full. So we have negligible actually ground vibrations because there is not much flowing water in this conduit. However, we deployed several monitoring stations throughout autumn and winter 2020 to see if we can capture the initiation of the flow in this cave and go and do the experiment there. And in addition to the monitoring seismic stations, we also deployed a weather station to record the atmospheric pressure and rain and wind data. And also we deployed 2 water level loggers at the entrance and resurgence point to do similar study as we did in Avoca River. So you see, and actually you're in the next slide, you're looking at the seismic data of the monitoring station near pull-to-fill entrance. So as you see, we don't see that persistent signal initially. When there is no flow actually in the cave. However, as days pass, so you're seeing the spectrogram for different days of the deployment. We see the initiation of the flow by appearance of this persistent signal on the spectrogram, which in this case is like a double frequency signal, and it's very interesting. So we left the seismic instrument in March 2021. And also here you see the data from the water level loggers. The top is from the pull-to-fill and the bottom is from the Puldillin rising. So we deployed the water level loggers mid-November and they were there until July. But as I mentioned, we have seismic data until March and July 2021 here in this case. And there, as you see, there is like a sharp change in the absolute pressure as the water level logger in the pull-to-fill entrance that has been mounted near the entrance has been washed away in 6th of January. And that's why we see like a sudden change in pressure in this data. So this is an ongoing study. We are doing similar actually analysis to correlate the seismic data in the monitoring station with the water level measurements that we have in this cave to see and to find a correlation similar to the surface river. So once we observed the initiation of the flow, we went back to this site between 29th and 30th of March. We deployed several linear profiles of geophones and also we deployed 2 seismic arrays. So we applied the method as we did in Roscommon site to different linear profiles that we deployed here. So you see the results of the linear profile near the pull-to-fill entrance. This is how the seismic data looks like in one of the stations. So we see the persistent signal belonging to the water flow in the cave. And when we applied the method, we noticed that the probable location actually comes from where we see this sudden change in the structure of the conduit. Probably there is like a sudden, like a fall or like a waterfall or just going deep when the cave goes deep. So it generates enough energy for us to detect the signal. And similarly for another linear profile in the middle of the conduit, which actually locates here, we could detect the subterranean flow seismic signature by our method. This is again where there is a sudden change in the conduit. However, for another linear profiles, we could not detect the signal, probably because it's deep and also probably it's too weak to be detected. However, when we did numerical simulation for a very simple Karst model, like a limestone bedrock containing a conduit as a horizontal cylinder filled with water and we excited the conduit by a seismic energy, we noticed the propagation of the energy through the conduit. So this motivates us to do an Ergon experiment in pole during rising. So the second day of this experiment was actually the Ergon experiment in the pole during rising. And the idea was that we send pressure waves and we investigate whether we can track the propagation of this pressure wave in the conduit, and if so, we can actually locate the conduit, especially where and in areas where the first approach doesn't work as the conduit is deep. So we actually did several Ergon shots, as you see by the spikes here on the seismic data and also on the spectrogram. So we applied what is called array processing. In this figure you see the seismic data of one Ergon shot. So this is less than half a second of seismic wave that is generated at the pole during rising. So we applied the method and we noticed that we can track the propagation of the wave front from the place that is generated along the conduit. Basically, we could locate the underground conduit by this method. And the second array, which was deployed in the middle, actually, of the conduit, as you see, the data is noisier because the seismic stations are further away from the source, which was the pole during rising. However, we could locate the propagation of the seismic actually wavefront again along the conduit using this approach. But actually the method works and can locate only the strongest data which is closest to the array. That's why it can't locate like the propagation initially from the place that it is generated. So in the next step, actually, very recently, we've been contacted by a private company to study the conduit that undergoes M18. And we noticed that, interestingly, it is the continuation of the conduit that we had already studied. So between April 4th and 5th, 2022, I mean, just like 3 weeks ago, we went for a site visit and to do a pilot experiment here. So we had access to the shapefile of the initial dived actually segment of the cave. So we deployed 2 linear profiles of geophone in the safe passage along M18 to see if we can really capture the seismic signal here in this conduit or not. So interestingly, we could capture the data. So as you see, we can see actually the signature of the data here. However, it's a bit further away from the shapefile location. So there are 2 possibilities. There can be some spatial error in the shapefile. And also, based on the literature review, it seems that we are dealing with a wide cave here. So here we are just looking at the point actually data, but the cave can be up to 15 to 20 meter wide here. So it's not surprising that actually we are locating the signal a bit away from the point shapefile. So my colleagues actually were in the field yesterday and the day before to do the experiment here. So again, we deployed a linear profile in the safe passage and 1 profile in the hill just next to the motorway, and also 2 linear profiles on the other side of the motorway. And we are looking forward to look at the data to see, especially in this area, if we can find where the conduit goes, because it can't be a straight, and it can go anywhere. And it's very interesting, but it's not a very easy actually site to study the conduit location here. So in summary, we through the river experiments that we did, we noticed that we could quantify the flowing water using seismic ground vibrations. And we studied 2 dived caves, 1 shallow and 1 deep, to ground truth our method and our algorithm based on the shapefile of the caves that we have. And in both cases, we noticed that the energetic water flow, especially in Roscommon and also in Gort, where we have a change in the structure, can generate tractable seismic tremor. And also we could excite the conduit and make it into resonance using Ergon to locate especially the parts of the conduit that was not actually possible to locate using our initial approach. We are working at the actually conduits undergoing M18 at the moment to see if we can find and track it in the areas, especially that we don't have the shapefile, and it's not divable basically because of the roof collapse. So thank you very much for your attention, and I'm happy to answer any question. Thank you.